Hi folks, welcome back to Applied Econometrics. This is Chapter 6, Multiple Linear Regression. All right, so in Chapter 4, we introduced simple linear regression, as you recall, where there was only one regressor to help predict our dependent variable. Now, in our common example across our chapters, we investigated the impact of the student-teacher ratio on average test scores. Now, evaluating the relative fit of our estimated regression, we noticed at the time a relatively low R-squared, which suggests that the independent variable we were controlling for, the student-teacher ratio, only explained a very low proportion of the variance that we saw in the dependent variable across test scores. Now, anecdotally, this makes a lot of sense since we know there actually are many other variables that are quite important which influence classroom test scores beyond simply the student-teacher ratio. Now, the question is, if we don't control for these other independent variables that are important to predicting our dependent variable, does our estimated coefficient then on the student-teacher ratio, does it really capture the causal impact of test scores? We really have to ask ourselves that question. Now, in this chapter, we're going to discuss then the role of omitted variable bias on our coefficient estimates and how to correct for these problematic models. An additional issue is if these omitted variables, which are contained in the regression error term, if you recall, are they correlated with our independent variables? We have to think about that. This would actually violate that first least squared assumption we talked about, I think, in Chapter 4, and impact the interpretation then of the coefficient estimates. Thankfully, there is a relatively easy solution. If you think that there are other variables that are important, that are inside your error term that you can control for, by all means, control for these variables if it's easy enough to collect this data. This is what we call multiple regression, where we control for several independent variables. Now, our agenda for today is going to be as follows. We're going to talk about omitted variable bias. We're going to discuss how to use the regression results to, again, estimate both causal effects and predictions. That's going to look very similar to what we saw in Chapter 4. We'll talk about the complications of multiple regression and OLS. We will discuss measures of fit, which again will be very familiar to you based off of our prior chapters. We'll talk about the sampling distribution, which will be particularly important when we tackle the next chapter. I think it's Chapter 7, in creating both confidence intervals and hypothesis tests. And then we'll discuss control variables and how they make their way into our regression analysis. So let's go ahead and start with omitted variable bias. Now recall, in our previous lectures, we were running very simple linear regression where we were controlling for but one regressor. Right? So the coefficient on that regressor was the target of interest. We were trying to understand the degree to which our independent variable impacted our dependent variable. In the previous class example, we were talking about the impact of class size on the average test scores. Right? So the coefficient that found its way onto class side was beta 1, and we interpreted this as the causal impact of increasing or decreasing, here just changing, class size and the either positive or negative impact that would have on the average test scores. Now, there was a main requirement for our coefficient estimate to have a causal interpretation, and one of those key requirements was that we had the expected value of u given x was equal to 0. This was our first least squares assumption. Now recall, what is u? U is the error term in our regression, and that contains a few things. It contains all of the omitted variables that influence our dependent variable that we did not control for, and it also will contain measurement error of our dependent variable. So with variables we're not controlling for just yet, in our simple linear regression, think about other variables that can indeed impact the average test score in a classroom. It might be teacher quality, it could be average family income, it could be regional factors. I mean, if we live in the Colorado Rockies and we have 10, 20, 30 snow days in a given year, that might play an influence on average test scores. Whereas in a state with sun and no snow days, they might get constant instruction. They might statistically do better on average since they didn't actually have any holes in their education. Now, these are terms we have not controlled for, thus they'll be in the error term. Now with the least squares assumption number 1, this assumption says that all of those variables that are contained in the error term are not correlated with our independent variable that we are controlling for. Here, it was the student-teacher ratio. Now, if it's the case that one of these omitted variables is indeed correlated with our independent variable, thus this right here will be non-zero, then unfortunately our OLS estimator will be biased, and that is quite problematic. To have an omitted variable bias that we need to take care of, two conditions must be true. Number one, if we're thinking about z as the omitted variable that happens to be in our error term, number one, z must be a determinant of y. Okay? If z is a variable and it's the color of the rainbow, that probably is not going to impact average test scores. It must be the case that a variable that we are not controlling for is impacting our dependent variable of interest. So it must be part of the error term. Number two, to violate that first least squares assumption, it must be true that this omitted variable is indeed correlated with the regressor that we are controlling for. So the correlation is non-zero, and that's problematic. That violates that first least squares assumption. So if both of these conditions are indeed true, we have omitted variable bias, and we need to solve this dilemma. Now going back to the test score example, again we have y, which is average test scores, and this is going to be equal to beta naught plus beta 1 times an x variable. X here happened to be the student-teacher ratio. And let's say we know that there are other variables that will indeed impact test score, and we want to identify whether or not these variables are indeed omitted variables that could have negative impacts on our coefficient estimates. So the example from the book, and it's a great one, so I'm going to borrow it, is talking about English language ability, whether or not a student has English as a second language. Are they ESL learners? The question is, this is a variable that we are not controlling for. Does it, number one, does it impact our dependent variable of average test scores? And then number two, do you think it's actually correlated with our regressor that we are controlling for? So number one, so talking about ESL, so students that have English as a second language, do we think that's a determinant of average test scores? Well, we know statistically that students that are testing in a language that is not their native language, they traditionally have more difficult times in achievements. So it is true then that this particular omitted variable will be a determinant of our dependent variable, here average test scores. And then number two, we need to think about, is there any correlation between students that have English as their second language and different class sizes? So the thought goes that immigrant communities tend to be less affluent, right? So their families are unfortunately not as wealthy, and thus these school districts traditionally have larger classrooms, right? So having an increase in number of students and percentage of students that have English as their second language traditionally are from poorer communities, and those communities can't pay for as many teachers, and they are unfortunately going to have larger classroom sizes. So in this situation, our z variable of English as a second language will be indeed correlated with classroom size, or the student-teacher ratio. So these are the two conditions that need to be necessary to have omitted variable bias that's going to modify the interpretation of our coefficients on the student-teacher ratio. So here we have beta 1 hat, unfortunately, will be biased. And the question here is, in which direction will it be biased? Will it be biased upwards, suggesting that it has a greater effect than in reality? Or will it be downward biased, suggesting that it has a lower effect than in reality? So let's talk about this first intuitively, then we'll look at the math, and hopefully they both come to the same conclusion. Now think about this. If it indeed is true that our English language ability, so ESL learners, this is indeed correlated with student-teacher ratios, we have here that there is a positive relationship. As the percentage of students that are have English as their second language, as this is going to go up, traditionally, the student-teacher ratio is going up as well. There's a positive relationship. So usually as one goes up, the other one goes up. Now, if we don't control for this in our regression, this means that there might be some undue impact that is being attributed to our x variable of student-teacher ratio that is not true. Right? So what we're going to see mathematically in a few slides is that when there is correlation between these variables, traditionally it is going to upward bias our estimates for the coefficients on the variables we are controlling for. Right, so we're going to have upward bias. So effectively what that's saying is that the variables that we are controlling for, it is inflating them and giving an unreal estimation as to their true impact on our dependent variable, right? Giving them too much credit and too much power. In reality, these controlled for regressors, here the student-teacher ratio, doesn't actually have as much impact if there is indeed an admitted variable that is biasing our regression estimates. Now recall from chapter 4 when we were talking about how the estimated coefficient beta 1 hat was an unbiased estimator for our true population parameter. This is beta 1. Now the equation to calculate beta 1 hat was this equation right here. And when we broke it down a little bit more, we recall that for least squares assumption number 1 to actually hold, that this term up here had to be equal to 0. And it was equal to 0 because we were talking about the covariance of x and u to be 0. Right? That was the number 1 assumption we said. We said the expected value of ui given x was equal to 0. We were saying there was no omitted variable bias. There was no correlation between any variables that were in the error term and the regressor that we were controlling for. Now, what if, unfortunately, what if it's actually not equal to 0? What if there is some type of correlation between these two variables? So here, we're going to have some covariance between the two, and it's not equal to 0. So for this non-zero covariance between both x and our error term u, let's substitute in this amount. This is sigma xu, and we're going to divide by the variance of x, which is this right here. All right, so we have sigma xu over sigma squared x, and we are going to, right here, we're going to multiply this amount, or this fraction right here, by sigma u over sigma u. And what that allows us to do, let's rewrite this right here. We're going to have sigma xu times sigma u over sigma x times sigma x. I just broke apart this right here, the sigma x squared, times sigma u. And we're going to group together, let me change this color, we're going to group together this right here. Right, so this right here is the standard deviation of our x variable. This is the standard deviation of our u variable, our error term. And up top, we have the covariance between x and u. And you may have seen that in your probability and statistics classes. That is the correlation coefficient between x and u. We're going to call that rho xu. So we're going to substitute that in right here. And then the numerator will have sigma u, and the denominator will have sigma x. And then we have this right here. Right, so in chapter 4, there was no covariance between both our regressor and our error term. The covariance was 0. Here, what happens if it's not 0? Then we have a problem. Because one of the lovely things about our beta 1 hat, it was that it was unbiased, meaning beta 1 minus beta 1 hat minus beta 1 was equal to 0, because this right here was equal to 0. If it's not 0, if it's actually a positive number, here sigma u over sigma x times rho xu, then we have a slightly a problem. Right, so if least squared assumption number 1 was true, again, e of u given x is equal to 0, there's no correlation between those two, then it would be true that beta 1 hat, our estimate for beta 1, would indeed approach in probability beta 1, which means we have an unbiased estimator, which is the greatest thing in the world. All right, but if it's not true, so if not true, then we have that our estimator beta 1 hat does not unfortunately trend to the true population. It's going to trend, it's going to go in probability to this true population parameter plus a bias term. It's going to actually add to it. So recall a few slides ago when we were talking about if we fail to control for an admitted variable, that is going to bias our coefficient estimator. It was going to upward bias our estimator. This shows that. Right, so we have beta 1 plus another term. It's increasing then kind of artificially the importance or the impact of beta 1, and by adding this term right here. This right here is our upward bias. All right, so here for an admitted variable, to have bias, it has to serve both conditions. It has to both be a determinant of y. It has to be a relevant variable that's going to definitely impact our dependent variable. But it also has to be correlated with our current regressor. So the correlation coefficient is non-zero, which means beta 1 will be biased. It is no longer going to approach in probability just beta 1. It's going to approach beta 1 plus this error term. So returning back and thinking about the classroom size impact on the dependent variable of average test scores, we know that districts that have fewer ESL students, they will do better on standardized tests. There's a connection there, and they will have smaller classes because they have bigger budgets. So if we do not control for this, we're going to have a conclusion that our class size is going to have a bigger effect than the true relationship. Right? So we have an over bias or we have an upward bias estimator. Quite problematic. Now the question is this reality actually observable in the data that we've been looking at in chapter 4 and now in chapter 6? Let's take a look. So what you have right here is a table that I swiped from the book. This shows the differences in test scores for California schools with both low and high student-teacher ratios. So instead of actually having the student-teacher ratio increase incrementally by 1, we're defining a dummy variable saying that we have small classes if the ratio is less than 20. So this is small classes. And if the student-teacher ratio is greater than or equal to 20, these are the large classes. So there's two groups, so that makes it a little bit easier to compare. And we're going to break down these scores by the percentage of English learners in the district. So those whose native language is not English. Now, when you include all districts and you do not break down the samples by English as a second language, or we actually saw this, I believe, in either the last lecture or one before, we saw the average test score in the small classrooms was 657. The average test score in the large classrooms was smaller, and the difference was 7.4. When we introduced the dummy variables in the prior lectures, this right here is the coefficient that we estimated as being the impact of small classrooms compared to large classrooms on average test scores. And we see the t-statistic in testing that difference is 4.04, which is north of our critical value of 1.96, which means this is a significant impact. Right, so this says when we only control for the size of a classroom and we break it down into small classrooms, into large classrooms, this suggests that small classrooms do indeed have a statistically significant positive impact on average test scores. That was the relationship that we found when we were looking at simple linear regression. Now in this chapter, we introduced the idea that there might be some non-controlled for variables that are indeed in the error term, these omitted variables, that are going to create a bias because one, they do impact our dependent variable, and then number two, they're probably correlated with our independent variable that we are actually controlling for. All right, so here we're going to talk about the impact of English as a second language and break this down into the percentages of students that happen to be English learners. So less than 1.9%, all the way up to greater than 23%, a few different categories in between. So observing some of these relationships and these results, we do indeed see that the districts that have fewer English learners, so that have a smaller percentage of ESL students, have higher test scores. So we can see that vertically in the small classrooms, we see small percentage of ESL learners have an average of 664. The small classrooms holding that constant with a greater proportion of ESL students have 636. So indeed, fewer ESL learners have higher test scores. And the same will ring true even when you just hold the classrooms constant with a large number of students compared to the teacher. So you have 665 versus, let's say, the large percentage of English student language students, that's a 634. We see again right here that when you have fewer English learners, this will lead to higher test scores. So this is that first condition that is necessary for omitted variable bias, that our uncontrolled for variable that may or may not be in the error term does indeed have an impact on our dependent variable. So here, that uncontrolled for variable happens to be the ESL percentages of students. And this shows that this variable that we're not controlling for does indeed have an impact on our dependent variable. That's that first condition, again, of having the potential for omitted variable bias. Now, the second condition was whether or not this omitted variable was correlated and had some positive covariance with our independent variable. Here, our independent variable was the size of the class. So is it true then for, let's say, lower, let's change colors, let's say green, for districts with lower percentage of ESL learners, do they indeed have smaller classes like we kind of stipulated? Right? Because we said that places with lower ESL percentages are typically more affluent and more wealthy on average, and wealthier districts typically have smaller classes. So is it true here that when the ESL percentage is relatively low, let's say that right there, that there are more classes that are small? Well, here we have 76 small classes versus 27 large classes. So that rings true. Is the opposite true as well? As we have higher percentages of ESL students, are those classes typically larger? Well, when we have greater than 23% being ESL students, we have 61 large classes versus only 44 small classes. So we see this correlation between the two is non-negative, is non-zero, which means that the two conditions necessary for omitted variable bias are satisfied here. So this is problematic. We have a variable that happens to be in our error term that is indeed correlated with our aggressor. So we have that E of ui given x is not equal to 0, which means that our beta 1 hat will be biased. Big problem. And that's a particularly big problem because when we were not controlling at all for ESL percentages, we found that the impact of small classes was relatively large. We said 7.4, that's large, and we have a 4.0 t-statistic. This suggested that this was statistically significant. But, let's change this to a different color. When you look at districts with comparable percent of ESL learners, so we look at just one category, let's look at this right here. So holding constant the percentage of students that are English as a second language, holding that constant, we actually find that this class size effect that was so large right here kind of goes away, at least statistically. So we have 665 for the small classes. We have 661 for the large classes. And the eyeball test says, yes, the small classes test better, but is there any statistical significance? What we do is we find the difference and we run a t-statistic and we compare that to our critical values. We find that the difference is 3.3 and the t-stat is 1.13. In this situation, we would fail to reject the null hypothesis. This suggests that I do not have enough evidence to suggest that small classroom sizes are any better than the large classroom sizes. The same will be true down here. There is a numerical difference between the means, but the t-stat is so low that we fail to reject our null. We can't statistically say that small classes are any stronger than the other ones. Same thing is true up here. Our t-stat is in absolute value quite small, and only right here at 1.72 when you have classrooms that are 8.8 to 23% ESL students, that right there is just weakly, very weakly statistically significant at the, the alpha is equal to 0.10, so at the 90% level, confidence level. But that's still very, very weak. So for the most part, it seemed like when we were just controlling for the classroom sizes, we said we indeed did have statistical significance, that classroom sizes by themselves were a positive influence statistically on average test scores. But when we control for this omitted variable, we're actually seeing that effect kind of goes away. Indeed, it's a small effect and frequently quite non-significant. Which means then the actual causal impact of small classrooms on average test scores was greatly inflated. We said that we potentially have an issue with an omitted variable bias, and that beta 1 is probably going to be upward bias. Well, right here this says the impact is 7.4. Not quite. We have that this causal impact is greatly over biased, unfortunately. Breaking down the data and actually controlling for the percentage of English student learners as their second language, we find that the class size effect pretty much goes away. So what does that say about simple linear regression, where we're not controlling for all of the important factors on a dependent variable, especially when some of these omitted variables are indeed correlated with our independent variable? We have biased point estimates of our coefficients. That is a statistical nightmare. Thinking about then our estimated regression and our causal impacts, or the coefficients that we're trying to estimate, unfortunately, we have that regardless of what your n is, regardless of your sample size, we're still going to have estimated coefficients that are biased. Increasing the amount of samples and observations is not going to change this bias, unfortunately. Now, because we have a bias estimator for our coefficient, that means, unfortunately, when we're thinking about prediction, using a regression, our predictions are going to be way off. They're going to overestimate the impact of small classroom sizes, which means that hypothetically, a school district is going to invest way too much money in decreasing a class from, let's say, 21 students to 19 students, thinking that they're going to see this great increase in average test scores. We see right now that the impact of our independent variable on our dependent variable of test scores is greatly inflated. That is a big problem. Now, this all kind of hinges on how we interpret causality. We like to believe that all of these coefficients that we're estimating indeed show the marked change of an independent variable on a dependent variable. That is our hopes. That's what we're putting all of our stock in. But the reality is this assumes a lot, okay? And all of these assumptions have to be true. Let's look at some of those assumptions in the next slide. So for beta 1 to be a true causal impact of our independent variable on our dependent variable, the following four conditions more or less need to be met. All right, you've seen us talk about this in the prior lectures. We need an ideal randomized controlled experiment. Right? So for this to be the true causal impact, all of these four informal conditions need to be met. Number one, we need perfect subject compliance. And we need no errors are reported. We need perfect data. We need perfect compliance. Okay. Then number two, we need randomization. This is the big one. Okay. The reality is students that find themselves in large and small classes are not randomly assigned. There are other variables at play that we are not controlling for that will dictate whether or not these students happen to be in the small or the large classroom. Often it has to be in which part of the country you're in. It could be the wealth of your family. There are variables we're not controlling for that means that these students are not in a random small or large class. That is problematic. Okay? In an ideal randomized experiments, we would have subjects randomly assigned to avoid these confounding factors, right? These omitted variables that we can't control for. In addition to having small classes, because we're trying to identify the impact of small classes on average test scores relative to large classes, we need that control group. Right? So having a control group permits the measuring of differential effects of the treatments. So sometimes this is problematic. When you're thinking about the efficacy of a drug, you're going to have half of the participants randomly, and then unbeknownst to them, get the treatments, while unfortunately the other half have to get no treatment or a placebo. Okay, there's some ethical challenges there, but when everybody and all the participants sign their waiver, they know that they're getting one of the two, although they're not sure which one they got. Okay, we need a control and a treatment to be able to compare these average mean effects. And then lastly, the experiment part of it is that the treatment is assigned and nobody has the ability to switch groups. If you could switch groups, then that is going to greatly modify the estimated causal impact of the independent variable on average test scores. Going back to our example of class size, the ideal then is if we could randomly assign students into small or large classes, which there's a lot of ethical issues there, because if you're a parent and you want the best for your children, you don't want your child going into the large class because that is going to maybe be detrimental for their future success. Right? So that would be a perfect world if we can make that happen. But parents, having found themselves in the control group of larger classroom sizes, they're going to do everything they can to get their child switched over. That is going to muddy the waters and negatively impact our experiment. But assuming we could keep students in those classrooms assigned to their treatment or their control, then measuring the effect of student-teacher ratios on test scores, that coefficient would be true if we can maintain this randomization. Because they would be randomly assigned and they would not be allowed to ever change, then all of the other variables that we're not controlling for in the error term would not at all be correlated with our independent variable of assignment to a large or small classroom. So in this idea, regardless if you're wealthy or poor, your likelihood of being in the control group of larger classrooms or in the treatment group of smaller classrooms is random. Okay? If you could dictate which class you would be in, then unfortunately, those non-observable variables in the error term then would be correlated with your classroom size, and then our least squares assumption 1 would fail, which means our coefficient estimate on student-teacher ratio would be upward biased, and that would be problematic. Now in the real world, students are not part of this eternal game of let's put some students in large classes, some in small classes. We know it doesn't work like that. Wherever you live, based off of your income, your education, everything like that, and a lot of things that are unobserved, that will eventually dictate the size of your classrooms. Right? So there are things in the admitted variables that we are not controlling for. That means random assignment is not really happening. Typically, most of the wealthy people of the world are in smaller classes, and most of the less affluent or the poor people of the world are in larger classes. So random assignment is not actually happening in reality. So again, looking at our potential admitted variable, this Z is the percent of English learners, right? So the ESL students. This does then unfortunately satisfy the necessary criteria for this admitted variable bias. Number one, we've shown in prior results that this actually will influence your average test scores. We said classrooms with lower amounts of ESL students traditionally have higher test scores, and classrooms with a greater number of ESL students have lower test scores. So there is that impact. And unfortunately, this admitted variable of ESL students is indeed correlated with the regressor. We said before that classrooms that have a higher percentage of ESL learners, they traditionally are from less affluent families. that have something to do with wealth, and those areas typically have larger classroom sizes. So this omitted variable of just ESL class proportions are having a direct correlation with our classroom size. So we unfortunately then have evidence then of omitted variable bias. So that is acknowledging that a big problem, but it doesn't mean that all is lost. There is still room and opportunity to still learn about the causal impact of classroom sizes on the average test scores. But we would have to control for this variable of ESL learners. So a solution here is to eliminate the difference in this omitted variable. We would need to examine, right here, the effect of classroom size among districts that have the same percentage of ESL learners. Right, so that is in that prior table where we're looking at line by line horizontally, controlling for that percentage. We were looking at the large classrooms and the small classrooms, and we were seeing, is there an impact of smaller classrooms on the average test score? But we would have to control for that variable. That is critical. When we don't control for that variable, we saw that the estimated impact of small classrooms was 7.4, and it was statistically significant. We know, however, that that is greatly inflated. That is going to be upward biased, and that is a problem. Now, the good news here is if the only actual difference in our omitted variable error term that we are not controlling for is the percentage of ESL learners, then all is not lost. What we can do is within each group or within each bucket of ESL learners, we can compare the mean difference between small classrooms and large classrooms and figure out at different levels of ESL learners as a composition of the classroom if there's any statistical impact. So to do this, we essentially are controlling for the effect of this omitted variable when we're actually estimating our variable of interest, the small versus the large classroom. Right? So the hope is here, can we control for this to have a confident estimate of our coefficient on the student-teacher ratio? Because before, it was overinflated, it was upward biased, and that was a problem. All right, so we have three ways to overcome this omitted variable bias. Number one, and this is something laughable, let us try to actually have a randomized controlled experiment where we indeed do assign students to small classrooms and large classrooms. Right? But we know that hypothetically, once a parent is going to find out which group they're in, and they might not like it, they're going to do everything they can to mess with the experiments, and thus this is rarely feasible. Also for social reasons and ethical reasons as well. We could, in number two, we could pursue the second option of looking at a table, breaking down the estimated impact of small classrooms at every level, let's say, of the ESL classroom percentages, but that requires a ton of data. And if these classrooms also have as an omitted variable other things other than just ESL learners, things that we cannot control for, then we are in a lot of trouble. Right? So this cross-tabulation method is not really feasible either. So goodbye and goodbye. Then we're left with one option, and thankfully it's a great option, is we can use a regression in which these omitted variables are no longer omitted. Right? If we can actually get a hold of this data and we can control for it, then it is now one of the regressors we are controlling for. It is no longer in the error term, and thus there is no longer any correlation between our regressors and our error term. Then that means that our least squared assumption number one would hold, and that our estimate of beta 1 would actually be confidently unbiased, which is exactly what we want. So, thankfully, this long story comes to a happy conclusion. Just control for this omitted variable and add it as an additional regressor. So no longer do we just have one regressor in our regression. We're now going to have multiple ones, and that will control and help reduce the negative impact of omitted variable bias. Let's take a look how including one or more additional regressors is going to change both our population regression and modify our interpretation of these coefficients. All right, so here we now have two regressors that we're controlling for, x1, and x2. These are our two independent variables, or regressors. We still have beta naught being the unknown population intercept that we're trying to estimate. We have beta 1 being the causal impact of a change in x1 on y if we hold this variable constant. And then beta 2 is now the coefficient on x2. That is the impact of modifying x2 by a little bit and its impact on our dependent variable. Okay, but holding everything else constant. And we still have an error term, and that contains everything that we did not control for, all of those omitted variables. What we can hope for is that none of those variables that happen to be in the error term are biasing any of our estimators. And recall, they have to satisfy those two conditions. Number one, these omitted variables have to influence our dependent variable, which seems likely, but thankfully the condition number two is they might not be in any way correlated with the regressors that we're already modeling. If they don't, then we can be confident with unbiased estimates of both beta 1 and beta 2. Now, to interpret these coefficients, thankfully it's going to be really easy, but let's talk about the y, just so you're comfortable with it. Consider the difference in the expected value of y for two values of x1 and hold x2 constant. Let's say x2 is not changing. Let's leave that variable alone. And let's change x1. Let's say it's an initial value. So it starts off at x1 initial, say x1 not. And then we modify it slightly by adding a little bit more to it. So we could have right here that x1 happens to be, let's say, classroom size. Initially it happens to be, let's say, 21 students. And then we add one more. And then maybe it's 22. So in the first population regression, we plug in, let's say this 21 right here, and this will help us estimate our y. If we slightly modify our x1 amounts, so let's say 22, we plug in this new value right there, and it's going to change y by a certain amount. Right? So it's not going to be the original y, it's going to be that plus or minus something, just depending on this sign right here. So this y hat right here is our initial value. This, let's say, y hat delta y is our new value. When we find the difference, when we subtract one from the other, the after minus the before, so after minus before, right? So take this equation right here, and from it subtract this equation. What we have left is just this. We have beta 1 delta x1. Now if you divide both sides by delta x1, what we have is that beta 1 then is trying to estimate the change in y for a small change in x1. Okay, holding x2 constant. This is critical. We said that these equations up here are relevant when we hold every other regressor variable constant. Right? So then this interpretation of beta 1 should look very familiar. It's everything else equal. If I modify x1 by a little bit, we're going to increase or decrease our dependent variable by a certain amount. That is what beta 1 is trying to estimate. Beta 2 will have the same exact interpretation. Beta 2, if you go through the same exact process, we're going to have that this is holding everything else constant, will be the impact on y from changing x2 by a small amount. And then last but not least, our estimated intercept will be the predicted value of y when our regressors are both equal to 0. So as far as interpretation, this is almost identical to what we saw when we had that simple linear regression, when we have that single regressor. Now, what does the OLS estimator for beta 1, beta 2, and beta naught, how do we calculate it? What is it trying to achieve? We have the same exact objective. We're trying to minimize the errors. Right? So we have our original data points of y, right? That is our actual observation for our dependent variable. And then we estimate beta 1, beta 2, and beta naught to be b naught, b1, and b2. This is our estimated. If you plug these into our regression, this is our y hat, yi hat. So yi minus yi hat is our error. This is our estimated error. Remember, ui hat is equal to yi minus yi hat. So this is the estimated error term, or the estimated residual. Effectively, how far is our actual estimate of yi hat away from our actual observation? Our goal is to minimize the number. I want my prediction for yi hat to be very close, minimally close, or maximally close to our actual observation of yi. So what the OLS estimator does then is we choose estimates for beta 1, beta 2, and beta naught with these Latin letters, so B naught, B1, and B2, choose these coefficients appropriately to minimize the sum of the square differences. Okay? This is identical to the logic that we had with simple linear regression. Unfortunately, well maybe fortunately for us, is this you cannot calculate by hand, right? Or it's insanely difficult. So thankfully, we can either use calculus or software to calculate this. This is going to help us yield the estimates for beta naught, beta 1, and even beta 2. So in looking at the relationship between the student-teacher ratio and test scores, you saw this regression a few times in prior lectures. When we were only controlling for the one independent variable, we found that the estimated coefficient on student-teacher ratio was negative 2.28. Now in this chapter, we said that in the error term of our population regression, if we do not include the percentage of students in the classroom that are ESL learners, that's problematic. It is number one going to be a variable that definitely does impact our dependent variable. That is condition one. And then number two, that emitted variable is unfortunately correlated with the student-teacher ratio. So what do we do? What was that solution? We just control for it. We include it in our regression. So we have this right here. Naturally, as we are trying to understand the relationship between all of our variables, if we include more regressors, it's going to modify our point estimates on our coefficients. Right, so that has changed, this has changed compared to before. So the question is here, what happens to the coefficient on STR? Well, we used to have a strong negative impact of negative 2.28, and we still have a negative impact here, but it has decreased a bit, hasn't it? Was this predicted? Right, so for right now, do not focus too much on the negative sign right here in front of it. Just think about the point estimate of 2.28 and now 1.10. We said if we have emitted variable bias, it's going to upward bias our estimates, right, in absolute value, okay? So whereas before we had 2.28, if we then include that emitted variable, and now it's part of our regression, then we're going to see that our coefficient estimate for this variable of interest here, STR, is going to decrease. We are reducing that bias. And here, there is a positive relationship between the percentage of ESL students and the student-teacher ratio. So that means that LSA number one does not hold with the simple linear regression. So what was the solution? We include this variable in our multiple regression, and then we no longer have an issue with our regressors being correlated with the error term. Since this variable is no longer in the error term, we are actually formally controlling for it. So because these two variables are indeed positively correlated and thus not equal to zero, this means that the original estimate in absolute value of the coefficient estimate on STR would be upward biased when not controlling for the submitted variable of the percentage of ESL learners. Right, so when we suspect that we have emitted variable bias, control for that variable and you will see that the estimated coefficients on your targeted variable of interest is most likely going to decrease. Okay, because initially it was upward biased and now it's coming back down to reality. It's going to, in close approximation, actually unbiasedly estimate the true population parameter. And that's exactly what we want. So in data, the code is going to look very similar to what we saw last time. We're indeed going to regress our dependent variable of test score on now x1 next to. We have the student-teacher ratio according to this data set. And we have the percent of ESL learners. And we're going to do, again, comma robust to control for the potential for heteroscedasticity. Right, again, I don't like saying that word. I'm going to try not to say it. So this is indeed a regression with robust standard errors. And we have the coefficients. We have the standard errors. And importantly, we have the p-values for each of those individual variables. So we have that student-teacher ratio is indeed significant at alpha is equal to 0.05. We have that the next one, percentage of ESL learners, is significant at alpha is equal to 0.01, so even stricter. And we still have a statistically significant intercept. Right, so we don't any longer have that this is negative 2.28. That was a strong impact that suggested if we increase our student-teacher ratio by 1, it would reduce on average scores by 2.28. Now, because we're controlling for this emitted variable, it's lessening the impact. Now, instead of negative 2.28, it's actually only going to decrease scores by negative 1.1 on average. The opposite is true as well. If we decrease our student-teacher ratio, we used to think that if we decreased it, that this would increase our scores by 2.28. Right? But in reality, the student-teacher ratio is actually not as strong as an indicator on an influencer on the test score. So we see here that it actually only truly has a positive 1.1 impact on the average test scores. And we'll talk about more about this printout a little bit later. Let's go ahead and move away from the state of regression outputs, which is really important for both causal interpretation of our variables and prediction. And let's talk about just the measurement of fit. To what degree do the variables that we're controlling for actually help understand our dependent variable? So everything here is going to be the same as what we saw in chapter 4. We're going to talk about the differences between our true dependent variable and our estimated dependent variable, and that'll give us our residual, or our estimated error term. The root mean squared error gives us good information in the same units as to the degree that our estimates vary from the estimated line. Okay, helpful to know. We said r squared is particularly helpful because it tells us the fraction of the variance of y explained by x. Right, so what that says is for the variables we're controlling for x, they explain a certain percentage of the variation in y. So when our dependent variable goes up and goes down, if r squared is equal to 0.2, then the the independent variables that we control for explain 20% of the story. Okay. Now, we need to introduce a new variable called r squared adjusted. So what this does is the reality is if we keep arbitrarily adding regressors into our estimated regression equation, artificially, regardless of not if those variables are actually truly important, r squared will keep going up every single time. That's problematic. So what we have is this term called r squared adjusted that is going to control for the number of estimators, the number of regressors that we're including within our regression. Now for r squared, we're going to have the same exact definition that we saw before. Right, so effectively, using the regression output that we've seen, it's going to be 1 minus the sum of squared residuals. Right here, that thing we were trying to minimize in the prior slides, divided by the total sum of squares. Okay, but an interesting reality is that, again, as you add more and more regressors, it is almost emphatically true that r squared will always increase when you add other regressors. So if r squared is really supposed to represent the true impact of your regressors on your dependent variable, it's problematic if I start adding crazy, odd, non-relevant regressors and it still increases our r squared. It pretty much means that our r squared doesn't mean what we think it means. Okay, so why is it that increasing the number of regressors is going to pretty much always increase r squared? It's never going to decrease it. Sometimes it might leave it unchanged, but most likely it's going to increase. And let's think about why. All right, so recall OLS. Right, OLS is trying to choose the coefficients for beta 1 and beta naughts to minimize the sum of squared residuals. That's what we saw about 2 slides ago. Now, let's say we add 1 or 2 more regressors, and let's say that these new coefficients on these regressors still happens to be 0. So if there's no actual impact via OLS on these new regressors, SSR is unchanged. But if the OLS software is actually going to have a non-zero coefficient on, let's say, x2, x3, and x4 for those new regressors, if it's choosing non-zero coefficients, it means it's because it's found new values that are going to reduce SSR even more. So if, let's say, the new regressor coefficients, beta 2, beta 3, and beta, let's say, 4, are all not equal to 0, it means that the sum of squared residuals is decreasing. Okay, it's decreasing even further more. If SSR is decreasing right there, if this is getting smaller and smaller, this fraction is getting smaller and smaller as well. If that fraction is getting smaller and smaller, then 1 minus that fraction that's getting smaller. So 1 minus a number that's getting smaller, that is going to be getting bigger. So what we have right here is if SSR is going to decrease if the sum of squared residuals goes down, which it will if we have non-zero coefficients on our new regressors, then R squared is going to artificially and pretty much always increase. So what we have is our adjusted R squared. Sometimes it's R squared with a little line on top. I've seen it R squared with a little A on the bottom. Just depends on the textbook. It corrects for this problem by penalizing for adding another regressor. Right? It's not a bad thing. It's definitely not a bad thing to add regressors to your estimated regression because you're trying to understand all the variables that impact your dependent variable. But what we know is statistically, regardless of not if those variables are real, if they're important, if they're even relevant, R squared will always, always, always go up without limit. So what we have here is we want to calculate something called the adjusted R squared that takes into consideration the number of regressors. So what we're going to do is we're still going to have 1 minus SSR over the total sum of squares, but we're going to multiply it by this new amount right here, n minus 1 over n minus k minus 1, where n is the number of observations, and then k is going to be the number of regressors. So if we have, let's say, y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus the error term, then we have 1, 2, 3 regressors, k is equal to 3. And we would plug that in right here. Now what we see is as k increases, as we have more and more, as we have more and more regressors, we know that SSR will go down. And if SSR goes down, then R squared will go up. Okay? But as k gets bigger and bigger, let's look at this coefficient right here. As k gets bigger and bigger, let's think about this. As k gets larger, because there's a negative sign, that means that the denominator is going to get, so denominator is going to become smaller. As k gets bigger, the denominator does indeed get smaller. As the denominator gets smaller, that means that the fraction n minus 1 over n minus k minus 1, that right here is going to get bigger. And if this gets bigger, if this number right here gets bigger, let's erase a little bit. If this right here increases, then it's going to increase this right here. And if this amount right here gets bigger and bigger and bigger, then R squared is going to become smaller and smaller. All right, so it is true because of this coefficient n minus 1 over n minus k minus 1 that our adjusted R squared will always be lower. Okay. Now, let me highlight this right here because it is true. Sometimes you see R squareds that are quite shockingly very close. So if n is large, and here, if n is in the thousands or the hundreds of thousands or in the millions, then subtracting k on the bottom is not going to make a big difference, right? So sometimes when you have insanely large sample sizes, the adjusted r squared is effectively the same, maybe slightly less than the r squared, right? But either way, large samples, small samples, we need to control for the number of regressors, because when you increase the number of regressors, r squared always goes up. So r squared adjusted penalizes us for more regressors, and it brings r squared down to something more manageable, more realistic. Now looking at prior results from chapter 4, when we had the single regressor, we saw that the r squared happened to be 0.05. Okay. Now, we know that including just the one independent variable was problematic because we had omitted variable bias. So what we did is we included this new term right here, the percentage of ESL learners in a classroom, and lo and behold, we have r squared going up. Okay. Now, if we adjust for the number of regressors, because now we have one regressor and two regressors, then we have k is equal to 2. We incorporate that into the r squared equation, and now r squared is slightly less here. So a question then that begs to be asked is, what precisely does this tell you about the fit of the regression in the second equation compared with the first one? Well, again, recall, r squared tells us the percentage of the variance of our dependent variable that our independent variables actually explain. Right, so what is that 0.05? That essentially means that when our dependent variable of test score goes up and goes down, our independent variable of student-teacher ratio, only explains 5% of that variability. But when we control for student-teacher ratio and the percentage of students that are ESL, this now can explain almost 43% of the variation y. So it explains about 43% of the story. So we're getting better and better. Now lastly below, why are r squared and r squared adjusted so close? So we have 0.426, we have 0.424. And again, the hint right here is on the multiplier. Right, that multiplier again was n minus 1 over n minus k minus 1. Here k is equal to 2. Which should indeed decrease r squared, and it does decrease it. But what's the other variable in this coefficient right here? Well, it happens to be n. So what do we have? I think in this data sample, we had a very, very large n. Let's give an example. Let's say if n is equal to, let's say, 10,000. Why not? If n is equal to 10,000, then this right here is equal to 10,000 minus 1. This is 9,999. On the bottom, we'll have 10,000 minus 2 minus 1. That'll be 9,997. Right, if you do 9,999 divided by 9,997, you effectively get 1. All right, so that coefficient on that SSR divided by TSS is not going to actually be too much difference. If it's not too different, then the r squareds are effectively the same. All right, something to keep in mind when you're looking at your regression output. Mirroring the progression in chapter 4, where we looked at regression output, where we talked about fit, and then we talked about assumptions that were necessary for confidence intervals and hypothesis tests. Let's talk about again right here, what are some of the assumptions that are necessary to interpret our coefficients as causal parameters? Right, so a lot of these are going to look almost identical. We're going to simply update them just slightly for the multiple regression case. So this one will go a little bit quicker. So we again have our population regression equation, where here, instead of having just 2 regressors, we have upwards of k regressors. We have a few assumptions, and the first 3 should look very familiar. Here we're going to have the expected value of our error term given our independent variables is 0. So there's no correlation, no omitted variable bias, no connection between our error term, omitted variables, and our regressors that we're controlling for. That's great. We also assume that we have IID data. We are assuming that there is no large outliers. And to know this, we need to plot our data. And then last but not least, we have no perfect multicollinearity. And we'll talk about that in just a moment. So condition number 1, where the expected value of our error term given our independent regressors is equal to 0. This has the same exact interpretation as in the regression with just a simple regressor. Essentially, if it's not equal to 0, then there is a covariance between our error term and our regressors. There's a relationship. But if we assume that there's actually no relationship, then we don't have admitted variable bias, so we can avoid that. Now, if this assumption, let's say, fails, and the expected value of ui given x1 all the way to xk is not equal to 0, then that means, again, there's correlation between the error and something we're controlling for. So there's something happening in the error that's messing with our assumptions. What do? We try to collect that information and we control for it. So the solution then is, if possible, include this admitted variable in the regression, and then we can say that this initial assumption is indeed satisfied. Now, sometimes, unfortunately, this admitted variable that's causing us problems is not directly observable, or it's difficult to control for or to observe. Right? So if we're talking about test scores, sometimes, and I think I'll talk about this in a few slides, sometimes we know that a parent's efforts at home in helping their children with their projects is a great indicator on test scores and assessments. But it's really hard for us to collect that information because that's it's private actions. Right? So sometimes another solution is to include a variable that controls for the admitted variable. So we're not going to actually incorporate that admitted variable because it might not be observable or collectible. We might have a proxy for it, right? Kind of like a little shortcut, but we'll talk about that soon enough. Assumptions 2 and 3 are nothing new. We have IID data, which means we have random samples and it's not messing with any of our foundational assumptions. Number 3, large outliers are rare. We saw, I think, in chapter 4 that if you have steady data points that fit really well with an estimated regression line, and you have only one data point that is a large outlier, that can greatly influence your estimated regression equation. So OLS is super sensitive to these large outliers. Right? One wrong typo, one mismeasurement can really mess up all of our results. So what's the good practice to have in mind? Check your data, have a lot of scatter plots, and try to avoid typos or coding errors. If you ever find a variable that happens to be an outlier, you want to study it and try to understand, is this a typo or is this a real data point? If it's a real data point and you cannot throw it away, then it needs to be part of your regression equation. But if you find that this is an outlier and there was some type of potential issue in collecting it, then I think we can be confident in throwing it away because it's going to unduly modify and impact our coefficient estimates, which would be a problem. All right, let's talk about assumption number 4. This one is the new one. This says no perfect multicollinearity, right? Quite the mouthful. And this condition is satisfied when, let's get the highlighter, when one of the regressors is an exact linear function of the other regressors. So some combination. So let's go to the very simplistic world. Let's say, let's go to another color, that we're trying to estimate the relationship between, again, test scores, the student-teacher ratio, and you actually make a slight mistake and you put the student-teacher ratio twice. All right, and you put your robust standard errors. All right, what we're going to see is, well, literally, these two independent variables that you're telling Stata to work with are identical. It's the same variable. This is an example where one of the regressors, let's say the first one, is an exact linear function because it's identical to this one. Right? When one goes up, the other one goes up at the same time because it's the same variable. When we do that, Stata softwares, they kind of blow up. right? You can kind of make a computer blow up when you're telling it that these two things are different, right? Thankfully, Stata has some thresholds in place that protect it from imploding. And instead what it does is it tells us that there is a variable of interest that is problematic. And here it's actually going to say it drops one of the variables. So if you ever have some regression output where it's dropping one of the variables, there's some problem with multicollinearity. Okay? With perfect multicollinearity, typically what happens is one of the variables that you're controlling for, you accidentally typed it twice. Now let's say we didn't drop it. Let's say we did not drop it. Remember, in a multiple regression, you interpret each of the coefficients as, right, this is the impact of this one variable on my dependent variable holding everything else constant, literally everything else. Well, let's say this is x1, let's say this is x2. How exactly do you estimate the coefficient in x1 by holding everything else constant? So when x1 goes up, when x1 goes down, how do you hold x2 constant when it's the same exact variable? And the joke is here, you can't. That's why Stata says, haha, good joke, we're dropping it and we're moving on. Now the sampling distribution of the OLS estimator, or the OLS estimators, right? We know that because we have a particular sample, that every single time we resample and we estimate beta 1, beta 2, beta 3, naturally we're going to get different estimates with different data, right? If we have the entire population and we sample the entire population with 100% coverage, then the estimator will be the same every time. But we don't have the population. We don't have the time. We don't have the means. And a lot of the times people lie to us. So we do the next best thing. We sample, and beta 1, beta 2, we estimate those as B1, B2. But this is going to have a particular distribution according to our assumptions. All right, so conceptually, a lot of the things that are above here are not going to change since what we saw in chapter 4, which is very convenient for us. We still have that our estimate for beta 1, so beta 1 hat, does indeed approach beta 1 in probability. This is assuming we have no violations at all for any of our assumptions. And then we have that beta 1 hat minus the expected value divided by the standard deviation is going to be approximately distributed according to the standard normal distribution, according to the central limit theorem. Right, so these statements hold for every single one of our coefficient estimates, which means this is going to be relatively simple to understand p-values and t-stats and the statistical significance of all of these variables. Right, so here, nothing has really changed from chapter 4 except we added a few more coefficients. All the other calculations remain the same. All right, so we're not going to do too much more with this content. This is more important for the next chapter, again, when we talk about confidence intervals and hypothesis tests. Now, moving back to multicollinearity, again, quite the mouthful, let's distinguish between perfect and imperfect. So we already saw perfect multicollinearity is when one of your regressors is an exact, pretty much replication of the other one. Quite often, it happens to be that you accidentally put the same regressor twice, or we have, let's say, an example of regressing test score on a constant D and B, where D is equal to 1 if we have small classrooms, and B is equal to 1 if we have large classrooms. All right, so effectively, we're trying to set up dummy variables, right? This is a 1 or a 0. This is a 1 or a 0. But we have two dummy variables that are trying to differentiate one condition. Now, this is a slightly different example of a perfect an exact linear function of the other regressors. We have down here, so I'll write this right here, bi is equal to 1 minus di. We have that when di is equal to 1, so when di is equal to 1, when we have a small classroom, we know that 1 minus 1 is equal to 0. Okay, we knew that it was going to be 0 because if it's a small classroom, that means that B1 or BI is not going to be equal to 1 because it's not a large classroom. There is an exact relationship between BI and DI with 100% certainty. right? So we have two dummy variables explaining the same exact situation. This is an exact example of perfect multicollinearity. So if you actually put two dummy variables to explain the same thing, right, large or small classes, you're actually going to find that theta is going to drop one of them again because it does not like multicollinearity, right? It messes with our estimates in our story. So based off of the prior example, where we had two dummy variables explaining one situation, right? A dummy variable should really be one piece of information that's differentiating between large and small or tall and short. If you have two dummy variables explaining this situation, you have too much information. Or actually, you're being repetitive, and that's problematic. Now we can see that. It's called the dummy variable trap. We can see that in the following example. Right, so let's say we have a set of binary dummy variables. So binary means they take the values 0 and 1. Right? If a condition is met, it's equal to 1. If a condition is not met, it's equal to 0. Good to know. And let's say it's trying to explain mutually exclusive and exhaustive examples within a high school. Right? So let's be simplistic. Let's give an example. Let's say we're trying to identify all of the students in a high school as freshmen, sophomores, juniors, and seniors, and maybe others, right, for the super seniors or people that came in from middle school. Right? So if you indeed include all of these as dummy variables, so you have one, so let's keep this simple. Let's say there's no other. Say there's no super seniors. Let's say there's 1, 2, 3, 4. If you have a dummy variable for every single one of those and a constant, then you again have multicollinearity. Theta will drop one of those every single time. Right? This is called the dummy variable trap. So instead of me telling you about issues, let's talk about solutions. Okay? So with the prior example where we had a dummy variable for small classes and a dummy variable for large classes, so small and large, you really don't want two explaining one situation. Drop one of them. Okay? The dummy variable turns on when it's a 1, it turns off when it's a 0. That is sufficient. That's doing what it's supposed to do. Same thing here when we have more categories. Dummy variable should tell us all the situations, but we can't be repetitive here. Right? So when there's only two situations, the small and the large classroom, we only want one dummy variable. Same thing here. If you have m groups, m unique groups, you always want m minus 1 dummy variables. So with the small and the large classroom, you don't want two dummy variables, you want 2 minus 1. So here, we would drop, let's say, one of the groups. Now, why that's particularly okay, right? It's not like we don't care about the seniors. It's, we know that if you have, so y is equal to, let's say, beta naught plus beta 1. Let's say we have a dummy for freshmen, and then beta 2, dummy for sophomores, plus beta 3, a dummy for, what's the next one? Juniors. If we stop right there, if we actually have a senior, then they're not a junior, they're not a sophomore, they're not a freshman. That means that this coefficient right here represents the average impact on our dependent variable from a senior. Okay, so just because we do not include them within our regression does not mean that we have ignored them. What we've done by dropping one of the dummies is we've made that interpretation of the coefficient something that makes sense. Now we can also instead omit the intercept, right? Maybe we don't actually have this right here. We have beta 1, dummy for freshman, beta 2, dummy for a sophomore, beta 3, dummy for junior, and let's say beta 4, a dummy for, let's say, senior. That would be okay. All right, so here, if we have a senior, then again, this is 0, that's 0, that's 0, and here beta 4 would be the impact of seniors on our dependent variable. All right, but if we have all 4 dummy variables and an intercept, then theta is going to throw one of them away. And what's problematic is theta is arbitrary. Sometimes it'll throw away the dummy variable that you want. Sometimes it'll throw a dummy variable away that you don't want. Right? You can't pick and choose, unfortunately. So you avoid that by always having m minus 1 dummies or omitting the intercept, whatever you want. All right, so let's drop this right now. Let's say we still actually have the intercept. So what are the implications then of option 1, omitting one group, or option 2, omitting the intercept for the interpretation of the coefficients? All right, so if we actually have this constant right here, this beta naught, then we can interpret, let's say, one of the other coefficients, let's say beta 1, we can interpret beta 1 as being the incremental effect of being a freshman relative to the base case of being a senior. Right, so we're comparing then that category, the additional impact of being a freshman on average scores compared to if you're a senior. Now, if instead we omit the intercept, then let's go with beta 3. So if this is gone now, and we have plus beta 4d senior again, I brought that back, then we can interpret, let's say, beta 3. Beta 3 would be the incremental effect of being in this category right here, everything else equal. Right, that's what you would have anticipated. So if there indeed is an intercept, then the coefficients are the impact of that variable compared to the base case. And the base case would be, well, that would be gone. We'd be going back to the base case of seniors versus just the direct impact. Right, so take some time, think about that. I think the textbook has a little info box. It's important to know when you want to keep the intercept versus when you don't want to keep it. Okay, statistically, not much had changed besides your interpretation of the coefficients. All right, so with this dummy variable trap, with this idea of perfect multicollinearity, this is usually a typo or a mistake that someone made, and there's an oddity in the data. Software will alert you. And by alerts, well, back in the day, computers would fry and, well, maybe not. But what they'll do today is they will arbitrarily drop one of the variables. So you'll have state regression outputs, and you're looking for the coefficients on 5 variables, and it says for one of them, dropped. And you might say, why? Well, you know why. There was perfect multicollinearity, and it didn't like it. All right, so go back, consider which variables you want to include. Did you make a mistake? And try to evaluate the best steps forward. All right, so the solution then is potentially modify your list of regressors to avoid this issue. Right, because it's going to drop one of the variables arbitrarily, if you really wanted the coefficient estimate on the second regressor, so let's say if you really wanted beta 2, but it dropped it, well, you're not going to be too happy. So go back and think about the other variables you don't care about as much, and you're probably going to have to drop them. Right, so we can talk about best practices in section. Now, imperfect multicollinearity is quite different from the perfect version. Right, the perfect version is I made a mistake. I usually included the same regressor twice, or there is a perfect linear combination between two of these regressors. There's something that's always constant about the relationship. Here, imperfect multicollinearity happens when two or more regressors are simply just highly correlated. I mean, what does it mean when two variables are highly correlated? Let's say this is x1, let's say this is x2. When one variable goes up, the other variable goes up as well. Maybe not in a perfect fashion. Maybe it's kind of like this. So we're not actually regressing anything. We have a scatter plot between x1 and x2. We see that in general, when one variable goes up, the other one goes up. These are highly correlated. Or it could be the other way around, whereby we can have a very strict downward sloping relationship between the two. These would be negatively correlated. When one variable goes up, let's say x1, we have x2 going down. Right? This is a significantly high correlation. Now, why is this particularly problematic? We say that every single one of the coefficient estimates is the impact of that independent variable on the dependent variable, but holding everything else constant. Well, if you tell me that x1 and x2 are, well, they're quite correlated, either in a positive or negative fashion, it's almost literally difficult to even fathom and understand How do I increase x1 by holding x2 constant? They move in the same direction at almost the same speed and the same magnitude. So we have right here that if two independent variables are highly correlated, it's really hard to quote unquote hold one variable constant. Right? So that means that our normal interpretation of these coefficient estimates is modified, unfortunately. We also find that this type of potential bias is going to result in large standard errors for one or more of the OLS coefficients. All right, so something to consider. All right, now let's talk about the very last new topic for this chapter. Let's talk about control variables. Right, so the reality is we have a relationship between one or more variables, and if it is the case that there is an emitted variable bias, that is going to really mess with our coefficient estimates. That's problematic. So we said, how do you solve that? You solve that by controlling for those emitted variables. If you can indeed estimate those variables, if you can collect that data, include them in your regression, and you can avoid all those potential issues. So let's say, for example, bringing it back to class size and average test scores, let's say our goal, our objective, is to have an estimate on the effect of test scores from changing class size, holding everything else constant. Right? What else is outside of the school's control? What happens at home that I cannot technically observe or measure? Well, we have outside learning opportunities that might add to the richness of your education. We have parental involvement in education, reading at home with family. All of these things are variables the school really wants to happen, but is not anything that they can directly control. Now, what would be ideal is if with these experiments trying to understand the impact of class size on test scores is if we can randomly assign smart and less smart students to large and small classes, poor and wealthy students to these classes. If we can randomly assign them, then we can look at the coefficients on student-teacher ratios as a causal effect. But the reality is that's a joke. That's never going to happen. Right? So we have then that our error term includes additional factors that are potentially correlated with our regressors. Right, again, so knowledge of English, we said the ESL learners, we have parental involvements, and if we can observe them, include them naturally. But a lot of these emitted variables are not anything that are readily available or easy to collect for school districts. So indeed, it is difficult to observe all of these emitted factors. Really, there's no systematic way that a school district can really measure the amount of not only the quantity of parental involvement at home, but also the quality. There's no way to actually have a metric for that. So what is the solution then? The solution is to include what are called control variables, which are correlated with these emitted factors that we cannot observe. So these are not observable and are impossible to collect, but which themselves are not causal. So this suggests if I could not collect a data points, information on parental involvements, because it doesn't exist, what I would do then is just try to have a proxy, something that's related with parental involvement, putting that in my regression to at least indirectly control for that emitted variable. That's the hope here. So control variables are meant to solve a problem. Right? If we cannot control for ESL learners, if we cannot control for parental involvement at home, we know that these are number one, variables that impact our dependent variable. Okay, not a problem. But if they are in any way correlated with, so if they have a non-zero covariance with our regressors, then we know we have biased coefficient estimates. That was a big problem that we saw earlier in this lecture. So these control variables, while they're not perfect representations of what we cannot collect, at the very least, they help us understand the causal effect, and they help us avoid emitted variable bias. So let's see that in the coming examples. All right, so up here, we have our student-teacher ratio, got it. We have our percent of ESL learners, and now we have a new variable, lunch percent. So this is going to represent the percentage of students that receive a free or subsidized lunch. Now you might ask, to what degree does subsidized lunch really have an impact on our test scores? Does that really impact my proficiency in the classroom? Not really, but what it's doing is it's controlling for income at home, right? I, as the educator, cannot readily observe the income of every student's family, and we know that income is greatly going to influence our dependent variable. It's also going to be correlated with our regressors. So if I can't control for it, then I'm going to have omitted variable bias, which is a problem, right? But thankfully, this one variable that is pretty easy for us to observe because we know which students are indeed getting subsidized lunches and breakfasts. This is only utilized by students with low-income families. So in this example, which variable is the variable of interest? Well, we're still fixated on the student-teacher ratio. That has not changed, right? Number two, which variables are control variables? Might they have a causal effect themselves? What do they control for? Right, so we talked about, again, including the percentage of ESL learners, and we can interpret this as probably having a direct causal effect because school is probably going to be tougher, right? School is tougher if you're an ESL learner. School is potentially easier or less difficult if language is your native language. But it also could be controlling for other things we cannot observe. Right? What's in the error term? Error term are family-specific variables and characteristics that we cannot control for. Well, we know that students that have ESL, that are English as their second language, they traditionally come from families that might be first or second generation within the country. They might be immigrants, and they usually have less money, which is going to impact their abilities to score well later. They can't get tutors. So it is quite possible that this right here is trying to control for the immigrant status of families, for the wealth of families. Okay, so it is quite possible that the percentage of ESL learners is both a causal variable, because it actually has an interpretation that we can understand, and it also might be controlling for something else that might be in the error term, plus UI. Now, what about lunch? Does lunch have a direct impact on test score? Some of you might say yes, some of you might say no. If you argue that having a well-balanced lunch, or actually just eating throughout the day and not worrying about hunger, does indeed lead to better attention and impacts in the classroom, then yes, then the lunch percentages would have a direct causal impact. But what we know is lunch percentage of those getting subsidized lunches and breakfast probably is controlling for the wealth status of families at home. So again, right here, this could be a variable that is both interpreted as a causal variable, but also as a control variable, just depending on how you're understanding the story with your data. Now again, the purpose of control variables is to, well, let's not beat a dead horse, it's to control for things that are uneasily observed, or we cannot observe them. Now, an effective control variable is one that when we include it in the regression, it makes the error term uncorrelated with the variable of interest. Right? If we did not actually include the ESL variable, that would have unfortunately been in the error term, and it would have been correlated with our independent variable of the student-teacher ratio, which means our least squares assumption number one would not hold, and our beta 1 coefficient would have been biased. And we want to avoid that, right? It would have been overinflated, which we don't want. If we can proxy for those variables, or we can include those variables, then that's controlling for them, and that will make our coefficient estimates that much more both reliable and efficient. So going back to this example right here, we're indeed including the student-teacher ratio, the percentage of ESL learners, and the percentage of students that are on subsidized lunch plans. The question then is, does this coefficient right here really mean anything? And if it does, what does it mean? Or does it actually have a causal interpretation? If so, what do you think it would mean? Well, we see that not the point estimate, but the sign on it. The sign happens to be negative, which suggests that as more students are part of this subsidized lunch and breakfast program, this is going to reduce test scores. So if an administrator wants to do the opposite, if they want to increase test scores, this would suggest then just driving the lunch percentage to 0. So take everybody off of this subsidized food program. That's problematic because there are students, if we eliminate this program, that will go hungry all day. This estimator equation says that if we do that, that will actually increase test scores, when we actually might argue that will actually do the reverse. It will decrease test scores because those students will go hungry and then they won't be able to focus on their learning, and that will negatively impact their overall scores. So it is quite often the fact that some of these controlled for variables might not actually have a direct and straightforward interpretation. So just be a little bit careful and don't rush at saying exactly what it does and how it impacts the dependent variable. So a word to the wise, it's great to have all of your data, plug it into Stata, clicking a button, run your regressions, but always be very careful with what your regression says and what it probably doesn't say. All right, to finish this up, let's look at an end of chapter exercise. This is going to be exercise 6.5. Let's talk about the particulars. Let's say that data was collected from a random sample of 220 homes in a community in 2013. Let price be the selling price in thousands of dollars. Let's say BDR is the number of bedrooms. Bath is the number of bathrooms. H size is the size of the house in square feet. L size is the lot size, which includes the backyard. And then age denotes the age of the house in years. And we also have a binary or a dummy variable, poor, that is going to be equal to 1 if the condition of the house is reported as poor. So unfortunately, you don't qualify your house as in good condition or poor condition. You have an evaluator that gives the green light or a big red flag, and you just have to deal with it on the market. Right? So that's a binary random variable that you do not control. Now, including those 1, 2, 3, 4, 5, 6 independent regressors, we then have the estimator regression. All right, so what we want to do in the next slide is we're going to interpret some of these coefficients. We're going to interpret the R squared, and we're going to understand what this model says and what it doesn't say. Now, personally, after undergrad, I got a degree in economics and mathematics, and I went to go work in the consulting industry, and in particular, the housing sector. All right, so what we would do is we would work with home builders in Orange County and Southern California, and we would take information about their selling points, their amenities, their characteristics of their domains, their homes, their apartments, and we would estimate regressions like this so we can understand the impact of another bedroom on the price they can sell their homes for, or the proximity to a park and how that might change the value. Right? All of these independent variables and how they impact the price, which is what the developer really wanted to know. Right, so this is effectively what was done in this example. A says, suppose a homeowner is trying to convert a part of their existing family room in their home into a new bathroom. So they're adding a bathroom, a +1. The question is, what is the expected increase in the value of the house? All right, so which variable are we looking at? We're looking at bath +1. Does anything actually change otherwise? Does the lot size change? No. They are actually converting one room into a bathroom, so actually the house size does not change. The age doesn't change. Nothing actually changes besides bath goes up by 1. And we see right here that we have a positive 23.4 as the estimated coefficient. So because the price is measured in thousands of dollars, this 23.4 on bath means that if we add another bathroom, it's going to increase the price that a home is going to sell for by $23,400. So we have 23.4 times 1,000. It's going to be 23,400. That'll be the answer to part A. All right, B says, suppose a homeowner now adds a new bathroom to their home, or it's to like the side of their house, which increases, so another bathroom, great, increases the size of their house by 100 square feet. So two things now happen. We have another bathroom and increases the size of the house. So the lot size did not change, the property, but the house size increased by 100. So we have for B is what is the expected increase in the value of the house? All right, so we're going to have bath is going to go up by 23.4. We're going to add to that the coefficient on house size is 0.156. We're going to multiply that by, well, we just increased the house size by 100 square feet. And that should give us about 39, which is $39,000. All right. So what we're doing is we're playing hypothetical examples, understanding a regression equation that looks at, let's say, all of the homes in a particular county or city, and understanding the degree to which each independent variable impacts the price of the home. Right? So you have people thinking about this all the time. If I update my kitchen, if I add another room to the house, if I buy out my neighbor and have a larger backyard, how much will it actually increase my price? Right? So it could increase it by a little, it could increase it by a lot, but what we use is data to estimate this relationship so that we can predict the future selling price. All right, so let's look at C. C says, what is the loss in value if a homeowner lets their house run down so that it's now becoming poor? All right, so for that one right there, we have that the coefficient on poor is 48.8, and it's a negative sign, which suggests if a house goes from good condition to poor condition, that C, the value will decrease by 48,800. And then last but not least, we have some other information up here as to the relative fit of the data to our regression. We have that r squared up here is 0.72. And actually, that's not just r squared, that's the adjusted r squared. And I want to talk about if r squared proper was identified as 0.727, I want to show you how it's derived to find adjusted r squared. All right, so it's simply just plugging in some numbers into an equation, but I want you to know what data is doing so you can actually understand the process. So D, how do we actually calculate r squared adjusted? So this is going to be equal to 1 minus n minus 1 over n minus k minus 1. We're going to multiply that by 1 minus r squared. Now the important point is here is what is n? Well, n initially was the number of homes that we observed. N is equal to 220. What is k here? Well, k is the number of regressors that were included within our estimated regression. We have 1, 2, 3, 4, 5, 6. So k is equal to 6. All right, so if we plug in the n, plug in the n, plug in the k, plug in the r squared of 0.727, just test it out at home, you should get about 0.719, which effectively is the 0.72. Right, so the takeaway is here, r squared adjusted will always be less than our r squared, and it's trying to control for the number of regressors, because every time you add another regressor, r squared proper, the normal one, will go up. So we want to adjust it for the fact that we are adding more information. Right, so r squared adjusted will be slightly lower. Now, does anybody hinge their careers on their r squared? No. What's the real difference between 0.72 and 0.727? Effectively nothing. But it's important to realize these numbers, these statistics, are calculated in a certain way, and they are, let's say, biased upwards as we add more regressors. Just something to keep in mind. All right, so that concludes this lecture. Let us know if you have any questions on multiple regression. All Or what we did today is we added additional dimensions as far as having multiple regressors, which means we're able to understand more of the relationship between our variables and our dependent variable. If we can understand more of the story, we can predict more of the future. Right, so multiple regression is the way to go. Omitted variable bias is a very serious issue, which we can control for, thankfully, with multiple regression. Right, so we showed a few tips and tricks and a few problems. Let us know if you have any questions at all in the lecture. And you can ask questions in office hours, section, or on the discussion forums. Right, let us know how we can help. Have a lovely day, night, everything in between. Take care.